There were three ways to do it, like the conventional way by doing time reversal and sliding the pulse stream. We found out that it's not that straightforward, it's complicated. So we did the tabular method and the matrix method, and they were way faster and easier. Now we'll do the continuous time convolution, and you'll see that it's not that straightforward also. And this one here, it has to be done through the convolution integral. And sometimes you're required to do a lot of graphics, like plotting the function to know the limits of your convolution. All right, so the convolution integral by definition is similar to what we did with the convolution sum. So previously we had from negative infinity to infinity, h of n, x of, I'm not sure what was the variable, n minus n of some other variable, tau minus n, whatever. Similarly here, we do a time reversal for one of the functions and slide it all the way to the left. And we start sliding to the right, and we look at for the overlaps, and the overlaps will be the limits for this integration. So you can either flip and shift x or flip and shift h. Now we've seen in the properties x convolved h is the same as h convolved x. So basically it's a weighted sum from one function to another. This is the convolution operator. We talked about it. I will talk about the systems at the end of this lecture. Basically, the relationship between the input, the excitation signal, and the system is the convolution operation. So the output y is the convolution or the result of the convolution between x and h. All right. So here are the steps, pretty much what we covered in the discrete case. You take one of the functions, shift and reverse, do the plotting, then you start by doing some certain sliding, and then you compute at each case. This expression, we rarely use it actually, because as I mentioned, it's better to do the plotting. And from there, you can get the limits of your integration. Because the only thing that will be different from like one convolution to the other is the limits of this integration. So here is an example here for illustration. You have h of t, a triangle shape function, and you have a rectangular pulse here. And assume that you want to do convolution between these two. So you can either flip h vertically, then shift it, or you can do the same with x. So here in this example, let's assume we flipped h and do the shifting. So here's for this example. So this is the original shape of h. If we flip it, it will be this rectangle, but starts from -1. Then you add this arbitrary variable t, like you are shifting all the way to the left, and the values from 0 to 2 here. All right, so when you do this convolution operation, you have this triangle keep sliding, and the variable here will be t. So the first overlap will happen at t equals -1, and you start like this. Then you'll do the convolution, and you evaluate this expression between this function and that function. So those functions are expected to be given to you mathematically. Like for this one, it's going to be 2, where t is larger than -1, less than 1. And this one, I'm not sure what will be the expression here, but it will be a -t plus 2 over 2. At 0 equals 2, at 1, okay, it's not 2t. So it's going to be -2t plus 2. Okay, so yeah, when you do the time shifting, it will be, the reversal, 2t plus 2. And you have all the way the shifting, and you start the sliding. It's not that straightforward. It requires a lot of math. Probably this simple expression or this simple example, if you want to solve it, it will take the whole paper. So to simplify the process for us, we'll focus on rectangular signals. So let's assume this is H and this is X. This one has a certain width, and same thing here, and starts from a certain point, ends at another, same thing here. So let's call it C, and this is D. So when you convolve H and X, what will be the output in this case? So this is going to be the focus in this lecture, is the convolution between two rectangular functions. Okay, that's another example here. As I mentioned, I'm not expecting something like this during the exam. That's a lot of work, actually. Yeah, here is just simplifying it. It's just giving you the bright side of it. But yeah, if you want to do this convolution between these two functions, it's going to be a lot of work. All right, so as I mentioned, we'll focus on the rectangular shapes. So let's assume two signals here, x1 and x2. X1 has a certain width, W1, and a start and initial point A, and the ending point is B with a certain amplitude, uppercase A1. Similar thing here, we have another rectangle with another variables, let's say, another width, another start and end point. The result of the convolution basically is going to be between, or the spans between the summation A and C and the summation B and D. So immediately you start by drawing this line. This is your starting point. This is your ending point. And it's going to be A plus B. And it's going to be A plus C. And this is B plus D. So that's kind of the first rule here. So yeah, the start of the figure or the graph of the result of the convolution start from A to C, A plus C, and it ends at B plus D. All right. The result of the convolution between two rectangles is going to be a trapezoid, with a special case when the width of both rectangular signals is the same. The result will be a triangle. So if W1 equal W2, the result will be a rectangle. Otherwise, a trapezoid. And the good thing about this trapezoid is going to be symmetric. All right, so let's see this slide. This one is kind of very important. It has all the information you need about your convolution. So you don't have to worry about doing the convolution graphically or doing them. You just have to draw the output and find the relevant values for any key points in the figure. Now, what are the key points in the result? The starting and ending point. So this is the start and this is the end. And we mentioned the start and end are basically the summation of the initial points as for the start and the summation of the final points for the end. And we have the point at the center. As I mentioned, it's a symmetric function, or the output is symmetric. So the center, and the center is given by this expression, A1 plus A2 plus B1 plus B2. So basically, the summation of all these values over 2. That's going to be the center of the convolution. Now, another key points here are the trapezoid has a horizontal line on top, and there is this edge here that marks this rising line with this straight line. So this value of x1 equals the center minus W1 minus W2, the difference between W1 and W2, and take the absolute value divided by 2. And another variable for x2, if you find this distance, it's going to be exactly the same, but here you subtract, here you add. So here we have subtraction, and here you have the addition part. Now the amplitude is going to be A1 times A2, the amplitude of the first pulse, times the amplitude of the second pulse, times the minimum of the widths. So I have this one is the first width. This is the first width. This is the second width, and you find the minimum, and then you do the multiplication. So let's do an example here. Take it to the whiteboard. Copy this part. All right, so assume that you were given this example and you were asked to find the result of the convolution between these two signals. First of all, they are rectangular pulses. So rect t over 2 convolve with rect t over 2 minus 1. All right, first of all, we have to know how to draw the rect function, rect of t. Rect of t basically is a rectangular pulse centered at the 0. And it's just t, so it's going to be negative 0.5 to 0.5. And if you recall from the tables, rect of t over tau negative tau and tau over 2. If I recall well, yeah. So in this case, tau equal 1. So it's going to be half and half. Now in this case, I have t over 2. So in this case, my rectangle is going to be from negative 1 to 1. Okay, so that's rect t over 2. So that's for the first function. Now the second function is shifted to where? Left or right? Minus 1 rect of t minus 2 minus 1 is shifted to the right by 1. So it's a rectangle goes from 0 to 2. Okay. So we have the functions. Each one has the amplitude 1. All right. I mentioned previously the rule is if I have two rectangles with the same width, the result will be what? A triangle. So here, rect of t over 2 convolved with the rect t over 2 minus 1, I'm going to get this rectangle. And it's, what do you call it? Not equilateral. A rectangle with two sides are equal. What's the name? I forgot the name. But anyways, this side equals this side. Now, what do you call it? What's our ساقين يعني we all know that. All right, now, so what are the key points? I need to find this spot, this value, and the center. Now, this value, we said that it's going to be the addition of the first two values. So here, rect of t over 2 starts from negative 1, and rect of t over 2 minus 1 starts from 0. So their addition will be what? It's going to be minus 1 plus 0. So that's the first point. Second point, 1 plus 2. So the first one is from negative 1, and the other one is 3. So I found the start and end of the convolution. Now, what about the value of the center? Center equal a plus b plus c plus d over 2. Let's double check. A plus a1 plus a2 plus b1 plus b2. a1, a2, b1, b2. So basically, is the edges of the triangle, the rectangular pulses, all added, divided over 2. So we can say average is just added, then divided over 2. And that equal to minus 1 plus 1 plus 0 plus 2. over 2. And the value will be 1. So negative 1 and 1 will cancel each out. 2 over 2 is going to be 1. So this point here is 1. Now the amplitude here, how much is the value there? It was, the expression was A1 times A2 times minimum of W1 and W2, the minimum between the width of two functions. So what was the amplitude of the first rectangle? 1 times the amplitude of the second rectangle, 1. What was the first width? So from negative 1 to 1, that is 2. And the same thing for the other rectangle, that's 2. So the minimum between 2 and 2 is 2. So the output here will be 1 times 1 times 2. That will get 2. So I will have a triangle goes from negative 1 to 3. And the center point here, that's not a center. The center is at 1. And the maximum value is 2. Let's double check with the slides. Okay, that's a different question. Product of t over 2, that's the one, correct? Minus 1. No, it should be from 0 to 3, so it's incorrect in the slides. It's going to be from 0 to 2. I think that question is also put here. The question was solved somewhere else. There we go, that's the one. Still 0 to 4. So where did we go wrong? Any idea? Where did we go wrong? Okay, so we have rect of t over of t. Yeah, so what is the proper way to do it? Shift and scale or and shift? First shift, then scale. Is that how we did it? You guys remember? He's even, but in the rules, do you guys remember or you forgot? We shift first, then we scale. In my solution, what did I do? I scaled first, then I shift. So that was the issue. Okay, you got the idea? So I'll keep it in the recording so we do not fall for the same error again. So I'll repeat the question. Okay, we did it wrong. Why? We shifted. Oh, sorry, we scaled, then we shifted. The proper way is to shift, then scale. Now let's go back to the whiteboard. Everything is in the recording, so I'm gonna erase everything and redo it. All right, so we agree that this is direct t over 2. We said that we shift, then we scale. So I have rect of t is going to be this one. Negative 0.5 to 0.5. Now, rect of t minus 1 going to be what? 0.5 to what? 1.5. Now we do the scaling. Rect of t over 2 minus 1. Now, when we divide over 2, we expand by 2. So we multiply these values by 2. There's going to be 1, and it's going to be 3. Right? Now we do the convolution. I have the first one from negative 1 to 1. So the first rectangle, negative 1 to 1, convolved with 1 and 3. So that's the 0. and that's the 0. All right, so let's do the convolution. As I mentioned, the result should be a triangle. The point here is the addition -1 plus 1, so that's 0. The point here is the addition 1 and 3, it's going to be 4. This one, this point here is -1 plus 0 plus 1 plus 3 over 2. -1 plus 1, sorry. -1 plus 1 plus 1 plus 3. So it's going to be 2. The amplitude here is 1 times the minimum of 2 and 2. So the amplitude will be here 2. Is it clear? So yeah, it's good to have such mistakes. Sometimes we go, let's say, to advanced concepts and we forget the basics. All right. All right, so this is the same exact example. This one here is the same one here. And here are the values. The amplitude at 2, it starts at 0, it ends at 4, and the maximum value is at, at the center is at 2. Let's add another example, because this one was 2 rectangles with the same width. Now let's try 2 rectangles with different width. So let's do the convolution rect of t over 3 convolved with rect, and let's add a shift here. Plus 2 rect of t over 2 minus 1. So let's do the first one. Rect of t is going to be this one. -0.5 to 0.5. Then we do what? Shift will scale? Shift. So rect of t plus 2 means what? To the left by 2 units. So it's going to be -2.5 and 1.5. Negative. -2. Then, yeah, -1.5. Here? Yeah, here 1.5. -0.5 minus 2. Okay. Because it shifted to the left, yeah. And -1.5. Then rect of t over 3 plus 2 means what? I scale by what? 3. So what does that mean? I multiply or divide? When you divide here, you multiply there. So when you divide, it's expansion. So you multiply. So it's going to be negative. The rectangle here, -7.5 to -4.5. Amplitude is 1. What about the width? What is the width for this rectangle? -7.5 to -4.5 is 3. So that's the first rectangle. Second rectangle, we'll start with the rect. Rect of t is better to start always from scratch, 0.5 to 0.5. Then rect of t minus 1 is shifted to the right, to the left, to the right. So it's going to be 0.5 to 1.5. Then rect of t over 2 minus 1, 1 to 3. That's the 0. So 0, 0. What about the width? Two, 3 minus. Okay, so what about their width? Are they the same? No. So the output should be what? A trapezoid. So previously, two of the same width, I got a triangle. Now I'm gonna get a trapezoid. All right. So I'm convolving these two functions. Here is my output. I'm gonna draw a trapezoid, and this trapezoid is symmetrical. Means that this is a center point. This half is a mirror image of that half. Now, what about this value? It's the addition of this and this. So negative 7.5 plus 1, negative 6.5. This value here is negative 4.5 and 3. So here I'm gonna get negative 1.5. All right. Now this center point. Actually, this, since it's center, right? So it's the point in middle between these 2 points. What will be the value? I will say it's negative 4. Let's do the expression. It's A plus B plus C plus D over 2. So A, negative 7.5 plus negative 4.5 plus 1 plus 3. Negative 7.5 plus negative 4.5 all by 2. So that's going to be negative 12 plus 4 over 2, negative 8 over 2, negative 4. All right. Now what will be, what else? This value here. And this other value there. So that's, we called it x1 equals what? The center minus the absolute value of what? Go back here. W1 minus W2 over 2. So we'll go here. What's this value? 3 minus 2. So 3 minus 2 over 2. So that's going to be half. At the center is negative 4 minus half. So negative 4.5. And this one here is what? Negative 3.5. Why? Because the other expression is going to be the center plus this same expression. So it's going to be 1.5. All right. And the last part is the amplitude. A1 times A2 times the minimum of W1, W2. So I have 1 times the minimum of 2 and 3, which is 2. So the value is 2 here. Huh? Okay, someone might say, okay, doesn't make any sense. The look of this trapezoid, like negative 4.5, and there is exactly negative 4.5 next to the negative 4. So this one should be wider. This is just an illustration. So these not exact values. If you want to draw, let's say, more accurate, this trapezoid will look like something like this. Yeah, that's more like the actual shape. All right, so that's it. Yeah, for convolution continuous time, these two expressions, and there is one example that will do it with unit step functions. But those are the major ones when it comes to convolution. We have triangle, we have a we have a rectangle, we have trapezoid at the outputs, and now we'll see one that we will actually do the convolution integral itself. Like I'll do the convolution itself. All right. Slideshow. Okay, properties of convolution. Something we probably already know since we did the discrete. So commutative, associative, distributive, so all something like you may consider convolution similar to multiplication, but it's not the same, but it has this similarity. Okay, so for any function, one of the properties when you do a convolution with delta, and that's what we call the impulse response, when you have the input signal delta of t, and you feed it to a certain system h, and you get the output h of t. In this case, h of t equals, sorry, the output y of t will equal delta of t, which is the input. That's x of t convolved with h of t. So in this case, we have the special property, anything convolved with delta is going to be that same thing. So in this case, y of t equals h of t. All right, so in this case, anything convolved with delta is going to be that expression. One of the properties, if the delta is shifted, so x convolved with a shifted delta, I'm going to get a shifted version of the function. So graphically, if I have a function like this, 1 and 2, convolved with an impulse at 3, what will be the output? Like graphically, if you have this convolution, the output basically, I'm shifting this function by 3 units. Why? Because I have the amount of shift is 3. So I'm going to get the same exact rectangle, but shifted version by 3 units. So I have 4 and 5. Is it clear? All right, so we've done convolution graphically a lot of times. Now let's do it mathematically. So for this following pair of waveforms, use the convolution integral to find the response y of t. In fact, when you think about it, if you look at this function, if you think about doing it graphically, you can never do it. Reason why these functions are not bounded. By bounded, I meant like when I have this rectangle, I know that there's a starting point and there's an ending point. And this one here, the unit step function, it goes up to infinity. Same thing here. It's for negative half of t, u of t also goes to infinity. So let's take these two expressions and try to solve this function using the integral. We'll do some plotting, but the solution will be for the plotting, just to find the bounds of the integration. Copy. All right. Also in the exam, I may give you some question like this, and the only thing I may change is this expression. All right, so we know from convolution, y of t equals x of t convolved with h of t, and that equals integration from negative infinity to infinity, x of tau, h of t minus tau, d tau. Or integration from negative infinity to infinity, h of tau, x of t minus tau, d tau. Means that you can either flip x and shift it, or flip h and shift it. Now, from these two functions, which one you think is easier to be flipped? Let's plot x of t. I have two elements, e to the power negative half of t. It's a decaying exponential, something like this, multiplied by u of t, multiplied by this part. And there is 0. So this part will be gone. In this case, I'm having this function. So this is e to the power negative t over 2 u of t. Just, the unit step function is just to remove the negative time, the points in the negative time. Okay, do you think shifting this one and, sorry, reversing this one and sliding it is that easy? Let's compare it with the other function, h of t. H of t is this one. This one is easier to flip and shift. So let's flip it. So h of, now we'll talk about tau, because my integration is this one here. So I'm using this expression. Why? Because I'm flipping the h function. So h of tau is this one, h of negative tau, something like this. Now, then h of negative tau plus t, which is t minus tau, is what? And here's the 0. What will be the value here? T. So I'm shifting to the left. Why? Because it's t minus tau. I'm adding tau. So I'm adding t. So I'm shifting to the left by t points. All right. Now this function here will be sliding until it reaches an overlap with this function. So first overlap happens where? When t equals what? So let me draw it. So I'm having this 0. This is t convolved with, or sorry, timed with this one here. So this point in time is 0. Where does the first, and this one is like a moving train. It just goes all the way to the right. So the first overlap happens when t equals 0. So my integration starts from 0. And let's assume that overlap kept happening at this point. And convolution basically is finding this integration. Is the multiplication of this and this. So what will be the other limit of the integration? I'm taking the integral from 0 to t. Now what are my functions? Unit step function is 1, and this is just e to the power negative t over 2 dot t. And that's it. Sorry, tau over 2 d tau. And that's the integration that you need to finish. As I mentioned, so in the exam, just keep it simple. It's going to be from 0 to t, and the only thing you need to worry about is whatever function I give you next to the other step function. Okay. Okay, so basically the convolution by definition, you pick one function, do flipping, and shift it all the way to the left. Then you start sliding that function over the other function to have an overlap. So in this case, I found first x of t. This is the function, the first one. And the other one is flipping, shifting. Now, what do I need to do with this one? Is sliding all the way over the time axis until it has an overlap with the other function. So when I did this, I have this function sliding, and I wanted to overlap with that function. So where does the overlap happen? At this value, t equals what? At the first overlap when t equals 0. So the first part of the integration is from 0, because by definition, integration from negative infinity to infinity. But because I'm using unit step functions, so I'm going to start from 0. That's the first overlap. Then this function is going to keep sliding. Where it will end? It will never. Why? Because the function is going to infinity. So it will end at t point, because I'm finding the convolution at any point in t. So in this case, this is my overlap. This t is coming from this function, and I have the 0, so I have the multiplication of this exponential by this unit step function. And the limits of my integration is going to be from 0 to t. So integration from 0 to t e to the power minus tau over 2, because I changed the domain for the integration, dot d tau. So when you do the integral in this case, negative 1 over 2 e to the power minus tau over 2 from 0 to t, negative 1 over negative 1 over 1 over 2. So in this case, negative 2 e to the power minus tau over 2 from 0 to t. Take the derivative, you will get that value. All right, let's substitute. It's going to be negative 2 e to the power negative t over 2 minus 2. So you're going to get negative minus t over 2 plus 2. When you substitute 0, that's negative 2 minus is going to be plus. And I assume it's going to be, this is the result of the expression. There you go. I can ignore the unit step function, but yeah. Plus 2 e to the power negative t over 2. Solve another question. Okay. X of t equal t square u of t, h of t equal u of t. Okay, so which one you want to reverse? This one. In fact, you just can't keep it simple. It's going to be from 0 to t squared dot dt. Tau squared dot tau. Like it's going to be the same procedure like the previous example, but the only function that changed is t squared. And there it was e to the power negative t over 2. So in this case, it's going to be tau cube over 3 from 0 to t cube over 3 u of t. We'll add the unit step function to keep it closer. Is it clear somehow? No. See, the whole thing for convolution, both functions, you change the domain into tau because of the integration. So h of tau, d of, like in here, well, x of tau, h of t minus tau, h of tau, x of t minus tau. So this one you consider it in terms of tau, and this is tau. But you can keep them as t. But because of, to be, let's say, more mathematically proper, you change the domain, because here t is considered as the shift, like the amount of shift. It's not the x-axis anymore. The x-axis now is tau. But it's not a big deal. It's like, I understand the way you're going to solve it. But to be mathematically proper, you have to change the domain. Get the idea? All right, so let's continue. And here is the output of this convolution. All right, impulse response, to keep it simple, output of the system, when x of t equals delta of t. It's basically impulse response. Is you apply an impulse, you get a response. That's the impulse response. Now, what is the special thing about the impulse response? Basically, the system characterization happened because of the impulse response or the impulse function. Now, why people apply the impulse function? If you recall from the previous lecture, the Fourier transform, where's my marker? The Fourier transform of delta of t equals 1. So if you look at the frequency, omega or f, it's going to be always 1. It means that it has a value over all range of frequency. Why do we care about that? When you design a system, have you taken electrons too? electronics. So when you design a system, you want to see the frequency behavior, how the system will behave against a range of frequencies. So you give it a signal that has all the frequencies, which is the impulse. And the output will tell you the response of the function for all range of frequency. So you can know if it's a low pass filter, or you've done filters, you've seen filters before, right? So you know it's a low pass filter, high pass filter, band stop filter, and so on. And let's say you design a system that is for audio signals. For us humans, our ears are sensitive to a range of frequencies from 300 to 20 kilohertz. So when you design a system, you want to know that, or you want to make sure that the output here is for this desired bandwidth, let's call it, or the desired range of frequencies. So this is the logic of impulse response. So impulse response for any function is h of t. Why? Because when you apply, here's the system, h of t, this is the unknown, that's something that we don't know. And I have my input x of t, and I have my output y of t. And we know the result is y equals the convolution of x and h. Now, what if x, my input, is the delta function? So what will be the output? Y, the output will be h. So whatever I'm getting is going to be the system response, the impulse response. So yeah, an LTI system is completely characterized by its impulse response. Okay. Step response, we don't usually, let's say, do step response, but in discrete domain, sometimes it's useful to get the impulse response from there, or you can get the impulse response by taking the derivative of the step response. So in this case, you apply a unit step function, you are getting the step response, take the derivative for this one, it will get you the impulse response. For practical reasons, sometimes getting the impulse, the actual impulse, like in physical hardware, it's not that straightforward, but getting a unit step is much easier. So get the step function, apply to the system, whatever the output, take the derivative. That's one way to find the impulse response in a practical manner. Okay, so block diagram representations, something pretty straightforward for LTI systems. So you can have them in cascade or series. So here you have H1 and H2, you do not multiply them. Here, you just convolve. So when you have two systems in series, their equivalent system is their convolution, or the result of their convolution, not multiplication. When they are in parallel, you just add them. All right, so let's consider this example, and I believe this is the last one. Determine and sketch the convolution of the following two signals. So you have x of t, t plus 1 from 0 to 1, and 2 minus t from 1 to 2, and 0 elsewhere. Find the output when the input, when you have h of t is delta of t plus 2 delta t plus 1. So let me take it to the whiteboard. Okay, so from the properties, we know that x of t convolve with delta of t minus t naught. Then this one equals what? X of t minus t naught. So if I convolve with a shifted delta, the result will be the convolution of the system with a shifted value. All right, so I have two parts of h of t. So when I have x of t convolved with h of t is basically x of t convolved with delta of t plus 2 plus 2 delta of t plus 1. Distribute the convolution. So I have x of t convolved with delta of t plus 2 plus 2 is a constant, x of t convolved with delta of t plus 1. All right, the result of this convolution is going to be x of t plus 2 plus 2x of t plus 1. Tamam? So here I'm shifting x by 2 to the left. I'm shifting x by 1 to the left and scale by 2. All right, so I got, let's say, the key facts of my function. Now, how does this function look like in plotting? So when you plot this, so let's assume this is t. Now, this function is t plus 1 from 0 to 1. So at 0, how much is the value? So I have the points 0, 1, 2, 3. So from 0 to 1, at 0, the value is 1. And at 1, the value is 2. So that's the first part of the function. The second part is 2 minus t. At 1 is how much? 2 minus 1. Because here, I want to plot the function. You guys, you know how I did this? Okay. So 2 minus 1, it is 1. So at 1, it is 1 here. T. So that's a 1 and that's a 2. So I'm getting a 1 here. And 2 minus 2, that's a 0. That's it. So I'll keep the key points to avoid confusion. So that's my function. Let's first find x of t plus 2. So I'm shifting this one to the left by 2. So it's going to be negative 2, negative 1, 0, 1, and 2. So at negative 2 is 1. It's that line up, and same thing here. And that's going to be plus x of t plus 1 times 2. So let's try to draw the one with minus 1. So I have negative 2, negative 1, 0, 1, 2. I'm plotting it so I can do the addition point by point. It will be easier this way. So the same function shifted to the left by 1. So here, something like this. And notice I'm scaling by 2. So this one's going to be 2. This will be 4, 2, 0, right? All right, so let's do the addition. It's going to be pointwise addition, something really easy. Okay, so let's assume this is the output. So I have negative 2, negative 1, 0, 1, and 2. So at negative 2, how much is the result of the addition? So basically, I'm getting this segment because there's no similarities with this one. So here, that's going to be 1 to 2. 2, 1, 0. All right, at negative 1, what will be the value? I have 2. And I have this discontinuity is here. At negative 1, let me, yeah, the amplitudes. So initially, I have negative 2, it's 1. Yeah, this one has to be the same. Yeah, 1 and 2. I'm basically adding these two segments together. 1 plus 2, 3. So that's the 3 here. 4 plus 0. Okay, do it this way, will make it easier. 2 plus 1, that's 3. Okay, probably my axis is not proper. Okay. Okay. -2, -1, 0, 1. Okay, so at -2, I'm adding these two parts. So there is nothing here, so it's going to be the exact same thing here. So that's going to be 1 to 2. 1, 2.
We don't count the
Here's zeros.
starts from -1, I want you to, so how would it be?
Okay. You're talking about this part, which function? The first, this one or this one?
We're adding one.
Yeah, so you add where we have, let's say, at the same time interval.
Okay.
So from -2 to -1. This is the segment I have.
Yes.
And there is nothing there.
-1.
-1, that starts from there. So this segment will overlap with that one. Okay, I know that you see, okay, there's a 2 here and there is a 2 here, so it should be 4. لا, this one belongs to that one.
No, that one is 1.
Like 2, high 1. So
we don't add them together?
لا, I'm adding these two segments together. So I'm having this segment. Now, same thing here, just add the edges. So I'm starting at -1, I'm getting 2. At -1, I'm getting 1, so I'm going to get 3. So there's a 3. 4 and 0, it is 4. So there's this line. And last, from 0 to 1, like in this one, if you want to consider 0 to 1, I have this value, and that value. لا خلاص, just look at this interval, I have this only function. Just add it. So from 0 to 1, from 1 to 0, like this. The value is 1 and this is 0. And that's it. And the value here is 4, right? Yeah, 3 to 4. 2 to 0 or 1 to 0? 1 to 0. Wait. 2 to 0. Yeah. Oh. Let's revise it. First, are we doing the shifting right? So it's going to be 1 to 2. Okay, and 1 to 0. That's the first part. The second one, 2 to 4. Then 2 to 0. This is shifted by 2 points. This is shifted by 1 point. Then we add by intervals. So 1 to 2, there is no overlap with that. Then here I have 1 to 0, 2 to 4, 2 and 1, that's 3. 4 and 0, that's 4. And lastly, I have this segment 2 to 0. That's the same. You saw.
The shifting, the second shifting. So we shifted.
Here?
We shift the original function, not
Yeah, the original function was shifted by 1 to the left. Yeah. So the original function is there. Shift to the left by 1. So -1, 1, -1. And we can confirm we are getting the same answer here. Is it clear? واضح؟ All right, so let's take a break. So when we come back, we'll continue with the other part of Fourier. Okay, so let's stop sharing. Stop recording. stop. لا ما راح يكون في لاب، لا راح استغل